I have read the press release and I was hoping to learn more about the design features and applications of the transverse flux motor. So, why don't we start by having you give your elevator pitch? Tell me a little bit about yourself and provide the context at ETM and Graco.
Yeah, absolutely. Thanks, Rahana. Yeah, transverse flux is a story that started in the 1980s. And if you do a little research online, you'll find that there were some university publications that happened at that time. There were some early designs and patents filed, but not really any commercial success or any really, relevant commercialization of the technology since that time. But even at that time, there was this promise of superior torque density and the potential of creating these direct drive motors or electric machines that had, superior performance in low speed, high torque, especially high duty cycle applications. The reason that was possible is that in transverse flux, and I'm going to show you a transverse flux stator piece here. So we're looking at a transverse flux phase, okay? And what you see here is a coil that does not wrap through the slots in the stator like you would have in a typical electric motor. Instead, the coil goes around the axis of the motor. And what that does is it creates a coil, which I have here, just a standalone coil, these coils that are very simple rings of copper. Okay, and because of that, you have much lower coil resistance in the stator, which means lower losses and higher efficiency. The other thing you'll see here is you have significantly higher pole count. So in a transverse flux machine, you have one tooth for every pole. This is a 60 pole stator. So a whole lot of poles for this size stator, which you would typically see in a radial flux machine, would be 4 poles, 8 poles, maybe 12 poles would be a high pole count. This one has 60. That gives you a lot of high torque performance at low speed and efficient operation, even at very low RPMs. And with transverse flux machines, you can actually design for efficient operation even down around 100 RPM. And this is unheard of in conventional radial flux machines. So then if you fast forward from the 1980s to 2007, there was this team working in Flagstaff, Arizona. And at the time, we did not even realize we were working with transverse flux. It took a few years to figure out that that's what we were doing. But we were working on this technology that essentially was all the features that we're talking about here, using conventional materials, no special, unobtainium or anything like that, just arranging them in a different geometry inside the motor. ETM made a significant investment in both the design and manufacturability of these motors to kind of take advantage of that early promise of torque density, but end up with machines that are actually practical to manufacture. And that took a lot of years. So here we are in 2026, and now, especially with ETM being a part of Graco, we have a lot of higher volume manufacturing where these machines are being produced in the tens of thousands annually on, in some cases, automated production lines. And yeah, lots of different applications that have been successfully commercialized.
How is the transverse flux motor technology influencing future motion system architectures? I've already heard quite a bit of innovation and requirements for shifting from where it was and how it can be used. So how is this technology now influencing motion system architectures compared to the traditional radial flux servo motors?
What we're seeing is a trend toward direct drive and a reduction in complexity in the gear transmission system, whether it be belts, planetary gears, strain wave gears, whatever the gear approach is. We have examples where the transverse flux technology has been able to come in and move a machine that was previously geared in a two-stage gearbox at, say, a 20-to-1 or a 30-to-1 ratio all the way to direct drive. That's not an easy thing to do, even with transverse flux. but we have commercialized examples where that's actually the case. And we also have numerous examples where we've done a 10-to-1 and converted that to direct drive. So that's the first thing, is just being able to simplify the gear train. The other is really being able to make a smaller, lighter system with higher efficiency, just because the motor itself has higher torque density and higher efficiency, especially at low speeds.
Yeah, and speaking of better efficiency, let's talk about energy efficiency. So with growing regulatory and ESG pressures really around energy efficiency, and also we're seeing a lot of electrification, of course. How does TFM technology position OEMs relative to the conventional permanent magnet and axial flux motor solutions? So what gains can we have in this motor then?
So in the world of IE efficiency regulations, there's incremental improvement that's available with standard technologies to move from an IE2 to an IE3, 4, 5, and we're continuing down that progression. But those are fairly incremental changes in efficiency for a defined system. If you really want to impact the energy efficiency at the system level, you have to address everything from the battery or the grid power source all the way to the end consumption of the mechanical output of the motor. So the best way to do that is to take a system level view of the efficiency and power consumption and the losses. And a lot of it shows up in the transmission. And oftentimes you'll see transmission efficiencies that are quoted at maybe the high 90s, mid 90s. It depends on the number of stages and the type of gearing or belting. What's not as typically explained is that's usually at some kind of optimum operating point. And when you move away from that operating point, you can end up with efficiencies that are really, not great. So 50% or something like this. It just depends on the technology. Transverse flux then can come in and impact the system level efficiency, including the transmission. So that's the first thing. And that's actually starting to show up in some of the new regulatory systems, is a system level efficiency requirement, including the power electronics and the motor and the transmission. So yeah, transverse flux plays well into that future.
Okay, very good. And I want to get a little bit deeper into the weeds with motion control systems. And as they are increasingly integrated with advanced servo drives, model-based control, there's a lot more in real-time diagnostics. A lot of emphasis is placed on that now. So what unique control or integration considerations arise then when you integrate TFM motors within mainstream motion platforms?
Yeah, what we're seeing is, especially in systems that are highly dynamic, the potential via eliminating transmission components and eliminating some of the reduction ratio, or even going straight to direct drive, you end up with less compliance in the system, less reflected inertia, less energy consumption related to that reflected inertia, because now your motor is spinning at a much lower speed. So your rotary inertia then passing through that transmission or direct drive is much lower. So if you can imagine, if you have, again, a rotor spinning around this transverse flux stator and it's direct drive at 200 RPM, imagine that inertia. And then imagine a motor that's about the same size, but it needs to go through a 10-to-1 or 50-to-1 transmission to achieve the same torque. You're going to have much higher rotational inertia in that system that's spinning faster. So that's the first thing in terms of step response related to just much lower inertia by running the motor at a lower speed.